Artemis I CubeSats, ready to invade the solar system. Okay guys, on September 3rd, there was another annoying postponement for the first Artemis mission. But we're almost sure by the time you're viewing this video, the Space Launch System, SLS for short, will have already taken the Orion capsule into space for its test run around the moon. And not just the Orion. The payload of Artemis I, in fact, is not only the technological innovations to be tested on their debut. On board the NASA rocket, there will be in fact also 10 CubeSats, small satellites comparable in size to a toaster, which will perform technology and science demonstration activities in lunar orbit. But not only that, we could call them all-purpose space drones, each with very limited tasks, but at an incredibly lower cost than the large and expensive probes that have made space exploration history to date. But what does this swarm of industrious bees look like? Let's take a closer look, shall we? Although CubeSats are now an integral and established part of the new space economy, it is only in recent years that their possible utility in the interplanetary domain has been understood. CubeSats are miniature satellites. Typically, they look like cubes with standardized measurements of 10 centimeters on a side. Their weight usually does not exceed that of 1 or 2 kilograms. Their structure is modular so that a CubeSat can consist of a single cube, or several cubes put together, generally up to a maximum of 6. Traditional satellites weigh 750 kilograms and up. This is no small difference. CubeSats allow for low-cost access to space, since launching a probe into orbit currently costs $14,000 per kilogram. This difference in tonnage, however, does not prevent CubeSats from doing almost the same operations as their big brothers. They can take pictures, shoot video, and receive and transmit data of all kinds. By now, CubeSats are revolutionizing Earth and space observation. Credit to advances in miniaturization of electronic components from sensors to antennas. The only handicap is autonomy. The average lifetime of a CubeSat is 2 years, compared with 5 or more for traditional satellites. The idea of granting space to a flotilla of microsatellites with the launch of the first Artemis mission was born in 2015 to provide access to lunar orbit for smaller universities and space companies. NASA initially intended to launch 4 more CubeSats beyond the current ones. However, the 3 teams responsible for these projects were unable to meet the October 21, 2021 deadline. In fact, on this date, the Orion was positioned above the second stage, making it physically impossible to intervene in the rocket adapter to add more CubeSats. This will also be a consideration for the satellites aboard the rocket. Having been aboard the rocket for nearly a year, some of them have not been charged, and there is a concern at NASA that they may not be functioning properly. In particular, the main doubt is over the first maneuver the CubeSats will have to perform individually, opening their solar panels. They will allow the batteries to be charged, but this first operation will have to be done with the charge remaining. But where are they located, and when will the CubeSats be released? Artemis I's 10 CubeSats currently have been aboard the Space Launch System for almost a year and are integrated above the rocket's second stage. To be precise, they are located inside the adapter that connects the second stage to the Orion capsule. The satellites, arranged circularly on the inner surface of the adapter, are individually housed in special release mechanisms. After the Orion detaches from the second stage, a very precise release sequence will begin that will last just over 5 hours. The first 5 CubeSats will be released simultaneously at 3 hours 40 minutes after the rocket's liftoff. The remaining 5 will then follow, separated one at a time at more constant intervals. The operation will conclude 8 hours and 3 minutes after SLS liftoff with the release of the CUSP CubeSat. Along with the 10 CubeSats present, 7 are made by US companies or research organizations, 2 by the Japanese space agency JAXA, and 1 by the Italian space agency ASI. Here are all of them below. Team Miles, the space belongs to everyone. This CubeSat, composed of 6 cubes and weighing 14 kilograms, is a demonstration of the potential of so-called citizen science, science done by citizens, Citizens who in this case managed to make it all the way to the Artemis launch pad. Team Miles, the winner of NASA's CubeQuest Challenge, was in fact designed and developed by a nonprofit group of 15 citizen scientists and engineered based in Tampa, Florida. The primary goal is to test innovative plasma and iodine thrusters. The minimum secondary goal is to get the probe at least 4 million kilometers on a trajectory to Mars, but the team will attempt to get it up to 96 million kilometers before the end of the mission. For comparison, the minimum distance from Earth to Mars is about 56 million kilometers. To get farther than any other vehicle of this size, the CubeSat will also test its software for radio communications with Earth. CUSP, a solar orbiter. Among the NASA-branded CubeSats is CUSP, CubeSat Mission to Study Solar Particles, which aims to study solar particles by orbiting the Sun. Specifically, the nanosatellite will analyze radiation from the Sun, such as solar winds and other phenomena that may impact terrestrial communications. CUSP will also be the pilot project to assess the feasibility of a network of CubeSats for space weather monitoring. The small probe, consisting of 6 standard CubeSats, weighs 10.2 kilograms. It will have 3 instruments on board: a miniaturized ion sensor, which will study the sources and mechanisms of solar energetic particle acceleration, a proton and electron detector, and a magnetometer. Luna H-Map, hunting for lunar hydrogen. The Lunar Probe Hydrogen Mapper is a miniature hydrogen hunter. Designed by researchers and students at Arizona State University, the CubeSat aims to study hydrogen abundances in shadowed areas of the Moon. It will fly over the Moon to a distance of about 5 to 10 kilometers from its surface and build a map of lunar hydrogen on a spatial scale of about 10 kilometers. The probe will be placed in an elliptical orbit whose perigee will be extremely low, between 8 and 20 kilometers. The proximity to the surface is a requirement born of the fact that neutron data at low altitudes can best characterize the distribution and amount of lunar water. The latter is data of enormous interest for future resource utilization by human missions that will visit the Moon. Lunar Ice Cube, in search of ice on the Moon. In 3 words, the slogan of this CubeSat is "Follow the Water." Developed by Morehead State University, Lunar Ice Cube is designed to sniff out water and other useful resources on the Moon. This will help future human missions to our satellite to make the most of resources on the lunar surface. The satellite will have a structure of 6 CubeSat units and a total mass of about 14 kilograms. Lunar Ice Cube will use an innovative ion engine to reach the desired altitude, which will enable it to make systematic measurements of lunar water characteristics from an orbit about 100 kilometers above the surface. The CubeSat will use a sophisticated infrared camera that is a smaller version of the one used on the New Horizons probe, designed with the wavelengths needed to distinguish different states of water, such as ice deposits or water in the liquid phase. Loon-IR, the Lunar Prospector. Loon-IR, or Lunar Infrared Imaging, is also a microsatellite intended to map the lunar surface. Its goal will be to provide additional data for the evaluation of lunar landing sites for future manned lunar missions. The satellite's main instrument is an infrared sensor that will enable Loon-IR to measure thermal emission and reflected sunlight from the lunar surface. The device, made by Lockheed Martin, weighs about 14 kilograms and is also a set of 6 individual cubes. It will map the lunar surface both day and night using micro-cryo-coolers, devices that will keep the temperature of the optical apparatus constant and allow the chamber to operate at much higher temperatures than normal for this type of infrared observation. The small cryo-coolers are described by Lockheed as the lightest and most durable ever deployed for the space environment. NEA Scout, the guardian of small and dangerous asteroids. Another important mission is the Near-Earth Asteroid Scout, planned by the Marshall Space Flight Center and the Jet Propulsion Laboratory. NEA Scout is a NASA project to develop a CubeSat composed of 6 individual cubes and equipped with an 86 square meter solar sail. that is capable of encountering NEA asteroids with a dangerously Earth-like orbit. The current mission target is asteroid 2020 GE, about 18 meters in diameter, but that could change depending on the launch date or other factors. After deploying the glider, Scout will perform a series of lunar flyovers to insert itself into the orbit that will take it to its final destination. The asteroid will make a close approach to Earth in September of 2023 at a distance of about 5.7 million kilometers. At that time, Scout will approach the asteroid up to 1.5 kilometers and perform the slowest flyover ever of a probe, only 110 kilometers per hour. A 14-megapixel camera, the mission's only instrument, will film the object at very high resolutions of up to 10 centimeters per pixel. The mission will demonstrate the ability of an extremely small spacecraft, powered by a solar sail, to perform low-cost reconnaissance of an asteroid. The goal is to develop a technology that fills knowledge gaps in ultra-small NEAs. Omotenashi, the world's smallest lander. Of all the payloads on Artemis I, the Japanese mission Omotenashi is certainly among the most interesting, since it will be the only one to land on the lunar surface. In fact, the Japanese CubeSat, consisting of 6 cubes and weighing 14.6 kilograms, carries the smallest lunar lander in history, 0.7 kilograms. The purpose of the JAXA, Japanese Space Agency, mission will be to validate microlander landing technologies and miniaturized propulsion apparatus. After separation from the second stage of SLS, Omotenashi will perform a corrective maneuver to enter lunar orbit. After 5 to 6 days, the lunar landing will begin, with the CubeSat performing a second engine firing to begin deceleration. When the action is over, a small solid propellant engine will detach from the orbital part of the satellite, taking the actual lander with it. After the release, the solid engine will fire for 15 seconds to slow the descent. Then the lander will eject the retro rocket, entering freefall towards the moon's surface. The impact will be cushioned using an airbag and a shock absorption system. The rest of the CubeSat, the orbital module, will later crash onto the lunar surface. Aquarius, radiation and meteorites. Also made by JAXA in collaboration with the University of Tokyo is the Equilibrium Lunar Earth Point 6U spacecraft, Aquarius CubeSat. Its goal will be to analyze space radiation around Earth. In addition to helping to better understand low-energy trajectory control techniques and lunar flybys in the Earth-Moon region, Aquarius could provide crucial information to protect electronics and astronauts during long-duration space missions. To perform these maneuvers for low-energy trajectories, Aquarius is equipped with an innovative vapor propulsion apparatus, consisting of 8 thrusters using about 1.2 kilograms of water. It also carries cloth on board, an instrument that will measure meteor flow in cislunar space using sensors that can detect the presence of dust. The results of this instrument may be of great relevance in understanding how the constant impact of meteorites on the moon may affect the future human presence on our satellite. BioSentinel, biological experiment. Also tied to astronaut health is BioSentinel, a CubeSat made by NASA's Ames Research Center that aims to better understand the effect of radiation on organisms in space. The mission will use a well-known ingredient here on Earth, yeast, which will serve as a model organism to understand how high-energy radiation can damage DNA. In fact, no laboratory on Earth is capable of duplicating the radiation typical of the space environment. Secondary objectives of the mission include testing the effects on the yeast of a solar storm. BioSentinel will be NASA's first experiment on the biological effects of radiation beyond low Earth orbit since the last Apollo 17 mission in 1972. Argo Moon, the official photographer. The Italian CubeSat Argo Moon will be perhaps the nicest of those aboard the mission. It will be the first to be released because of the task it has been assigned. In fact, Argo Moon's main purpose is to stay close to the SLS upper stage, photograph it, and then film the release of the other CubeSats. The images it will take of the second stage on its way to the moon and then release of the CubeSats will be historic and important. Argo Moon will then test communications between Earth and the CubeSat, and will also engage in photographing the Earth and the Moon. One of the main innovations of this satellite is the onboard software, developed by Argo Tech. In fact, Argo Moon, once released into space, should be able to automatically detect the upper stage of SLS and move autonomously in its vicinity. The onboard software will also be used in the second part of the mission. Once the main mission is completed, the satellite will turn on its engine several times to enter a geocentric orbit with high eccentricity. This means that Argo Moon will still be orbiting the Earth, but in its apogee. It will come very close to the Moon, close enough to be able to photograph it with great resolution. And there you go. That's it. Between now and the end of the year, we will have a lot to enjoy. And it will not only be about following the vicissitudes of the Orion capsule, but also all the extraordinary and exciting adventures that this little satellite swarm will not fail to get into.